Hi, good day to each and everyone. For today's video, we are going to talk about one of the fundamental topics in physics and mathematics, and that is vectors. Understanding vectors is very essential in analyzing motion, from forces to the movement of a certain object, and etc. So sit back, relax, and enjoy a moment of science with me. For today's video, we are going to focus on vectors. I will divide this lesson into two parts. The first video, we will focus on vector analysis using component method, and on the second part is we will focus on solving vectors involving the use of trigonometric functions. Now, let me just remind everyone that the focus of this discussion is limited only on the analysis of motion in one or two dimensions, and in particular we will focus on the usage of the component analysis and at the same time the use of trigonometric methods in solving for resultant vectors for this particular topic. So without further ado, let us now start with our lesson. Now, for many instances, we would like to ask what's the difference between a vector and a scalar quantity. Now, we have heard of these terms in many of our discussions in physics, but let's try to deal with them in particular detail. When we speak of vectors, these are quantities that has both the magnitude and direction. Whereas when we say scalar, that means these are quantities that have magnitude only. So there are lots of sample quantities that are vectors, one of which is of course force. Then we also have your velocity, then many other examples of vector quantities. I will leave you the task to research them on your own. Then of course we also have some scalar quantities like, for example, speed, distance. So those are some examples of scalar. Now, why do we need to know both of these types of quantities? It's because that knowledge itself will help us somewhat identify what are some of the correct operations that we need to use when we deal with the addition and subtraction, or even other operations with these quantities. So, for instance, if we are going to add and subtract vectors, now it would be very easy for us to add and subtract vectors if they are located only on one dimension. So for instance, if the motion, or shall we say the quantity that is being described is happening only on the x-axis or maybe in the y-axis, then it would be much easier for us to analyze motion in this case. So for example, if I'm going to draw something here right now, so for instance that a certain person walks, let me just use a black ball pen here. Okay, for instance, there's a person that walks at this particular direction to the east, let's say at vector 1, which is around, let's say, 5 meters to the east. Let me denote the direction because it's very important when we describe vectors. They should have direction. Okay, now upon walking 5 meters to the east, he decided to go back to his location. Let's just say he moved back at, say, 2 meters to the west. The question now is, what would be our resultant vector in this case? That is our unknown here. Now, when we add or subtract vectors, we have to be vigilant with the direction of where these vectors are pointed at, because depending on the direction where they are pointed at, that will determine in what operation we are going to use. So to somewhat make it easier for you to remember these directions, of course, always remember that we have a Cartesian plane wherein we can always track our directions. So for instance here, of course, we have here the north, we have here the south, we have here the east, and we have here the west. And always remember that in a Cartesian plane, we can also assign values for or sign for the integers. If we are going to the east, of course, that's taken as a positive value. Going to the west is negative. Going to the north is of course always positive, and going to the south is always negative. So that will help us remember in many cases about the directions of where these vectors are heading. So for our particular example, since they are both or both of these vectors that we are giving are moving in the opposite direction, then that would mean that there will be subtraction of vectors in this case. And in most cases, my dear students, the larger vector will always somewhat, how do I call this? The larger vector will always somewhat, we will always follow the sign of the larger vector of the two. For example, in this case, I have here the resultant vector is 5 meters plus, but 2 meters is pointing to the west, so I have here to write negative 2 meters. So therefore, this is the same as writing as 5 meters plus, sorry, it's not plus, but minus, okay? Minus 2 meters. So therefore, our resultant vector here would be around 3 meters. Now, what would be the sign of our vector here? So since the larger vector is having a positive value, then that would mean that our resultant vector will also follow the sign of the larger vector, in this case vector 1, 5 meters to the east. So that's how we usually subtract or add vectors in many cases in our examples. Now, as what I've said, it would be very easy for us to add or subtract vectors if they are only happening on one dimension. So if they are both moving or happening in the same direction, then technically there will be an addition of vectors for that. But if they are moving in the opposite direction, then there will be subtraction of vectors for that. So those are some of the things that you need to remember. Okay? Now, of course, vectors do not always happen in one dimension. In most cases, they happen in 2 dimensions. Let's say, for example, that a certain person walks, let's just say, 3 meters to the north. Okay? Because it's going up, 3 meters north. And then decided to make a turn to his east at around, let's just say this is 4 meters to the east. So, in this case, how do we find the resultant vector for this example? Well, in order for you to find the resultant vector for this example, we need to apply what we call as the tail to head method. So, what is tail to head method? Well, it simply means that we need to trace the resultant vector from the tail of the first vector, in which in this case is the 3 meters to the north. The tail of this first vector, which is here, I'm gonna mark that with red, and the head of the final vector, which in this case 4 meters to the east. Then we draw a straight line from the tail going towards the head of the second vector. And in this case, this will be our resultant vector for this example. So this resultant vector right now will have a certain value in which we can calculate using very simple theorem in mathematics. In this case, we call it as the Pythagorean theorem. Recall that in a Pythagorean theorem, using our example here, right triangle, let's label this. This is our right triangle. We have here, of course, our right triangle has a 90 degrees angle in one of its vertices. So, in a right triangle, the longest side is what we call as the hypotenuse of the triangle. So, I'm going to call this as the hypotenuse I don't know what's the correct spelling, so let's just label it as H here. So kindly search for the spelling. I'm not familiar with the spelling here. I'm not good with it. So H here. Then of course, the shorter leg I will call that as A. Longer leg we will call that one as B. Okay. Now, for us to find the hypotenuse of a right triangle, we need to use what we call we need to use what we call as the Pythagorean theorem. By the way, let me just change the label. It's not H rather, but it's C. Okay, because to make it somewhat the same as with the books that we are currently using. Okay, so C here is your hypotenuse, A is the shorter leg, and B is the longer leg. So when we apply the Pythagorean theorem, we know that the Pythagorean theorem states that the side C square, to obtain the side C, we need to apply this formula. C squared is equal to A squared plus B squared. And of course, if we want to really simplify this equation, apply square root here so that you can cancel the square root for the C. So that would mean C here is equal to the square root of the sum of A squared plus B squared. So that is what Pythagorean theorem is all about. Okay? Now, going to our example here for our first problem, the person walked 3 meters north and 4 meters east. Then, what is now its resultant vector? So, using the Pythagorean theorem, we can solve the resultant vector as follows. The resultant vector now would be the square root of the sum of the squares of the two vectors given. In this case, 3 meters squared plus 4 meters squared. Okay? So, we know that 3 squared is, of course, 9 meters squared. And of course, we know that 4 squared is 16 meters squared. And we know that when we add the two numbers together, they will equate to 25 meters squared. And of course, we know that the square root of 25 is 5. So our resultant vector here would be 5 meters. So that would mean that the resultant vector in our diagram here is 5 meters. Now, to solve for the direction, or shall we say the angle of the direction at which the resultant vector is pointing, now we need to use another important trigonometric relationships, and that is of course involving our right triangle. So to solve the angle of which this resultant vector is pointing, first we need to know the trigonometric function relationships. Okay, first allow me to transfer to the other sheet so that it would be much clearer for us. So let's just say that we have a right triangle here, and that we have a given angle here, which I will call as your theta. Okay, let me call this as your A, let me call this as your C, and let me call this as your B. Okay, so we now have this particular right triangle here. The angle is here, there. So if we have a given angle in which in this case lies between the side A and C, so we can actually solve for the sides given a certain angle using this very important relationship SOH-CAH-TOA. So that would mean here that for SO, that means it's sine of the theta, which is equal to the opposite over hypotenuse. Then we have here for ka, that is for the cosine function, that is cosine theta is equal to adjacent over the hypotenuse. And of course, we have TOA, which is for tangent of the theta, which is equal to the opposite over adjacent. Now, what does opposite, hypotenuse, and adjacent mean here? So in this particular example, opposite means it's the opposite side of the angle given. So in this case, our opposite side here is our side B, because that's the opposite of our angle. Okay? Now, for adjacent is the angle or is the side that is beside the angle. In this case, our adjacent side here is our A. Now, what is hypotenuse? Well, as what I've said earlier, hypotenuse is the longest side of your triangle in a right triangle. So in this case, this is our hypotenuse for C or C. This A here is our adjacent and this B here is our opposite for this case. So therefore, substituting the variables here, that would mean that sine theta would be equal to B over C. Then cosine theta would be equal to A over C. And then our tangent theta would be, of course, B over A. Okay? So, why is it that we need this relationship? Because it would be very important for us to solve for the angle at which this resultant vector is pointing. So, going back to our previous example, as you can see here, there, oops, my pen just fell. So, how do we get the angle now of our vector? So, if I'm going to go back to our illustration here, I know that my vectors are pointing north and to the east. So, therefore, the direction of my resultant vector should be in the northeast direction. So if I'm going to draw that in a Cartesian plane, it would be like this. Allow me to use another sheet for that. So if I'm going to draw another sheet for it, it would be going to the north. That is, how much is that? That's 3 meters. This is 3 meters. And then going to the east, that is 4 meters. And I know that my resultant vector is pointing at this direction, okay? Which is, of course, I know already that's 5 meters. We solved that a while ago. So, what will be the angle of the direction it is pointing? Actually, to solve the angle of the direction, you can actually use either of the two sides of the angles that are available here. You can calculate the angle which is here on this direction, and you can also calculate the angle that is here in this direction. And when you add those two angles, they are actually complementary angles, so they will add up to 90 degrees. So we can actually solve those two angles there depending on our comfort, no? Okay? Now, for example, in this case, if I want to know the angle at which my vector is directed following the two vectors that are given, then I'm going to use this angle side here that I am highlighting right now. So if I'm going to calculate the angle there, that would mean that the opposite side that I have right now, I'm going to draw something there. My opposite side now would be this one, 4 meters, and my adjacent side would be the 3 meters. So therefore, after labeling that, I will now be able to calculate the angle of my direction. You can use either any of these trigonometric functions. They will yield the same answer. But for me, in this particular example, I'm going to use the tangent relationship. So I'm going to write now tan theta, which is equal to my opposite over adjacent. So opposite over adjacent. Okay? So I know that my tangent theta, my theta is still unknown. So I'm going to write now what is the opposite of this side here. My opposite now is 4 meters divided by my adjacent side, which is 3 meters. The units will be cancelled here. So my tangent theta would be equal to, so if you plug that in your calculator, 4 divided by 3, that would be equal to 1.333 infinite series. There. Now, that is not yet the angle that you need to solve. So in order for you to solve the angle here, you need to apply the inverse of the function of this angle, inverse of function of this value here, and that will give you around, if you want to know how to get the inverse of the tangent there, you input the value 1.333, then you press shift and then press the tangent function in your calculator, then that will give you a result of around 53.13. So that would mean this is 53.13 degrees. Okay, so 53.13 degrees. So that would be my angle right now. But since my direction is on this side here, that is 53.13 degrees east of north. Okay? So, for my final answer right now, my final answer would be 5 meters at 53.13 degrees east of north. Let me box that one so that we'll have our final answer. Now, you might be asking, sir, will it be okay if I will get the angle on the other side of the triangle? Well, as what I've said, it's okay. It depends on your comfort, where you are more comfortable in solving for the direction. But of course, if you are going to solve for the angle here, which I am highlighting right now, the direction will not be east of north anymore. It would be north of east. Okay? Take note of that. Now, for you to easily remember the directions of your vectors in a 2-dimension, I have actually created and devised a way for you to easily remember this direction. I call this in my class the flower of direction. So, let me just use other pens here. So, if for example, I have a vector, a resultant vector here, I'm going to call that V. Then, I'm going to also create another resultant vector here, V. I'm going to create another resultant vector here, V. And another resultant vector here, V. So, for example, if the given angle is here, then that would mean that this is the direction of, this is the north of east direction. If the given angle is here, that is the east of north direction. If the given angle is here, then the angle there, that is north of west direction. If the angle given is here, that is the west of north direction. If the angle given is here, then this is what we call as the S, south of west direction. If the angle given here is on this side, then this is what we call as the west of south. Now, if the angle given is here on the southeast side, then this side here, given angle here, that is what we call as the south of east. And the angle that is given here is what we call as the east of south. And that will complete our flower of direction for easier reference. Okay? So you can use that one if you want to calculate for the direction or the angle for a certain direction. Okay? Now, I will end my discussion at this point. Now, for the second part of our video, we will deal with solving for resultant vectors using what we call as the component method. We will also discuss in the second part another way of solving the resultant vector, in which in this case, we will also be using the trigonometric functions. So, I hope that you have learned something out from our discussion for today's video. So I hope that you will keep practicing in solving problems involving vectors so that we will be able to master it, and we will have full confidence that in whatever problems that we are going to solve involving vectors, we'll be able to solve them more confidently. So this is once again Mr. Rabino. Goodbye and see you for our next video.